Okay, the last thing we want to talk about in this chapter is the concept of relative motion, and I have added a bunch of terms to the end of this title. It is a form of analysis to relate motion of one particle to another using the relative measurements between the two. And I want to focus on also the concept of translating axis, meaning that there is no rotation of one particle relative to another is considered or included here. If there is that kind of rotation, things become a little more complex. So we are only considering translational aspect. So what is the goal here? Imagine you have one frame, and there's one particle moving happily along a path. And you have another particle, another point, another observer moving possibly along a different path. And imagine you are sitting on this second particle and you're moving with it. So what you see, what you measure about the motion of the first one is something that is different from the actual. Let me try to change colors. Let's make this red. Let's make this one green. The actual position of the particle relative to the main observer, the fixed frame, is going to be different from what you observe. But if we have information about where you are and how you're moving, we can use the combination of this relative measurement and the known motion of the observer to find the actual motion of the moving particle, the particle of interest. So let's be systematic and define our system, our coordinate systems. Let's call this one the main frame, O, X, Y, Z. Let's call it, use capital, no, not necessary. X, Y, Z. And we have another coordinate frame that is attached to a secondary moving particle. Moving with it, it is X prime, Y prime, Z prime. X prime, Y prime. This is X prime. Sorry, it's a bit small. Now here is the situation. The motion of the main particle, let's call it, or let's describe it with position vector R. What this moving observer measures is another position vector. Let's give these ones a name too. Let's call this point B and this observer A, and that should have been O prime. Sorry about that. So this observer sitting at A, moving, measures a position vector of B relative to A. That's how we show it. And the particle A, or observer A, also itself has a certain position vector. So let me call this also RB, position of particle B. And we want to find motion of B knowing motion of A and relative measurements. That is the entire goal, but it is fairly easy to work at the position level. Position. We can just look at the vectors. Our goal is to find RB. And if you notice the triangle that these three vectors make, vector RB is essential vector RA plus this vector R of B relative to A. And that is our relationship. If we have the measurement, relative measurement of particle B from the perspective of particle A, and known information about the position of particle A, we can uniquely and quickly find position of particle B. That's easy. What about velocity? Velocity is equally easy if you take time derivative of this. We know velocity of B is time derivative of position of B. And taking time derivative of the right hand side, I have time derivative of position of A, that is position of, what do I write? Velocity of A, plus, as it turns out here, the relative position, if you take time derivatives, that gives you relative velocity, whatever the observer A measures from the velocity of observer B. So this is called relative velocity of B relative to A. And this one is absolute velocity of A and B. Let me do this. Absolute velocities of A and B. Velocities of A and B. And that one is relative velocity. And finally, accelerations. You can guess it. Acceleration of B is acceleration of A plus acceleration of B relative to A. And similarly, the first two terms are absolute acceleration, and the last one is relative acceleration of B relative to A. So if the observer sitting at A has these information about positions, velocities, and the acceleration of particle B relative to the observer A, and we have information about absolute motion of A, we can find absolute motion of B. Or in many cases, we can basically mix and match. We can have information about A, information about B. We want to find the relative motion, or if we know any two of them, the third one can be found. And this looks trivial, but actually it immensely simplifies the problems, because, for instance, consider an example of a double pendulum. You might have seen the videos of it. Let's call this point B, this is point A. Point B can have quite complex motion. It is really hard to, in one go, describe motion of B. However, if we note that at any time motion of A is just a circle around this fixed point, and motion of B is always, at least relative to A, just a simple circular motion about A, combining these two known information about these simple motions can very easily and a lot more conveniently describe the complex motion of B. So we see not double pendulum example, but a lot of other examples in class how this can be used in practice. So I think that is all. Let me see if I have anything else to say. Really not. That is all. The rest are seeing these equations in practice and how they can be useful. And yeah, that is all I have. That is the last video of this chapter. We end it here, and soon we will start looking at the relationship between motions and forces, and that is the topic of kinetics. So until then,